Well, of course they are not the same, right? The hydrogen discharge to produce light, which is a bit orange. The mercury discharge tube, on the other hand, produce light, which is a bit blue, right? Obviously, they have different frequencies. So just now, what is in the experiment is called emission spectrum of hydrogen and emission spectrum of mercury. So the emission spectrum of hydrogen or mercury, they are both in the form of line spectrum. They are both in the form of line spectrum. And indeed, different elements, they will produce different line spectrum. They have their own very characteristic emission spectra. They have their own very special fingerprints. And now let's take a look at these pictures. So you can see the emission spectrum of hydrogen. Alright, there are only a few lines here. Alright, while the emission spectrum of other things such as neon, then there are a few more lines. And then that of mercury on the right hand side, alright, different, right? So that's what I say. I said they have very different fingerprints. These spectra tell us what they are. And there are, on the other hand, also absorption spectra, absorption spectrum as well. Alright, let's take a look. Just now what I said. You get a light source and then it passes through cool gas. The cool gas will absorb some of the light. And then when the light remained pass through prism, the prism will then produce a absorption spectrum like this. This is called absorption spectrum, and then you can see some dark lines on the background of colored spectrum. So let's go back to the book, alright, see what the book say. So there is continuous spectrum when it is a filament lamp. However, when light pass through iodine vapor or any other cool gas, then frequency are absorbed, and then the remaining light is going to produce a absorption spectrum, and that's why you can feel a few, alright, dark lines in the absorption spectrum of iodine vapor. Right, so far you have learned something like continuous spectrum, line spectrum, emission spectrum, absorption spectrum. So at that time, would you please take a look of my book, alright, on the left bottom corner, and then would you please copy that down, alright, when I am explaining to you. So all in all, we have spectrum of different kinds. Spectrum, it can be line spectrum, many lines. It can be continuous spectrum, just like rainbow. And then for line spectrum, it may come from a emission spectrum, that is a discharge tube. And then it can also be an absorption spectrum, which is a continuous colored background with dark lines. And how can we have a absorption spectrum? It is from a light source, such as a filament lamp, and then the light passes through vapor, cold vapor, alright, and then it will produce absorption spectrum with colored background and then dark lines on it. Well, you may now turn to the next page and see what the book says about these. So on next page, alright, there we are. You can see in the middle there is a diagram. So the diagram is important. Let me go through the diagram with you. First of all, there's a hot source. It may be a filament lamp, it may be the sun. And then the light can pass through the diffraction grating directly, and so you can see a continuous spectrum. However, when the light is first of all passed through cold gas, and then this cold gas molecule in the middle, they will absorb some of the energy, some of the light energy. So certain frequency of light are absorbed, and then they are irradiated. The light molecules absorb the energy, and then they will irradiate the energy to all directions, alright, without keeping the energy. So then some of the frequency are irradiated, alright, in this and that direction. So the forward direction that goes to this diffraction grating will be one with less intensity of light in this absorbed frequency. So that's why it produces an absorption spectrum, because some of these frequencies are absorbed and re-radiate in other directions already. However, if you put a diffraction grating on that side, then you may receive the re-radiated light. The re-radiated light, alright, they are of special frequency. So you will have a emission spectrum. Okay? Well, the most important part is the gas molecules here absorbs some of the frequency of light and then re-radiate to other directions. So in the forward direction, there will be less light of this frequency, and that's why they are darker or dimmer, D-I-M-M-E-R, alright, lines produced on the spectrum. On the other hand, if you look at the light from the two sides, alright, observe from two sides, then you may have an emission spectrum. Okay, so the bright line in the emission spectrum have the same frequency as those of dark line in the absorption spectrum of the same element. Well, I find this, alright, in internet that show me different absorption or emission spectrum produced by different elements. So you can see this is now hydrogen spectrum, and then I can also get helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and different, alright, other elements as well, even metals such as mercury, such as silver, gold, alright, we have their different emission spectrum. You may also want to see the absorption spectrum. Basically, they are the same. Emission, absorption, same position. Exactly. Alright, this is then sodium. Absorption spectrum, emission spectrum. Now let's take a look at example 1. You can see example 1 have given to you 4 different emission spectrum, alright, of these 4 different elements: hydrogen, helium, lithium, and carbon. And as I said, these are different fingerprints. They are just fingerprints. So next page, please. Now here comes 2 unknown sample, A and B. So what A actually is, what B actually is. So what you have to do is you look at the patterns, you look at the positions of the lines, and then you may know what they are. Alright, so would you do the comparison yourself? And hopefully you can find out the solution yourself. You are a element detective. Well, so you may start to understand why people can tell there is a lot of hydrogen on the sun, because we may analyze the light from the sun. We may find the spectrum from the sun, and it is indeed, alright, this scientist called Fraunhofer, who studied the spectrum of light from the sun, and then he find that there are some dark lines. So people call those dark lines Fraunhofer lines, and later on we discovered that some of the Fraunhofer lines are indeed the characteristics lines of line spectrum of hydrogen. And so we start to understand the sun has a lot of hydrogen up there. Similarly, that's how we may also tell there is a lot of helium also on the sun. That ends the first part of the chapter, but then we now move on to the more important part of the chapter called spectral series of hydrogen spectrum. You know what? Hydrogen is already the simplest atom, and yet it's quite difficult, alright, to analyze its spectra. So at the beginning, they have, the scientists, they have a hydrogen discharge tube, and then they begin to analyze the hydrogen spectra. And then they even try to find the exact frequency and wavelength of the light emitted from a hydrogen discharge tube. They believe that there must be some kind of rules behind it. So the first scientist, which is Balmer, alright, he find it out is the Balmer series. So Balmer identifies some of the lines. these lines with wavelength 410, 434, 486, 656. These wavelengths, they are so closely related. Balmer find the equation that related them. Alright, so that's the equation that may relate them. So you may substitute n to be 3, to be 4, to be 5, and then in that way, using the equation, you may find 410, 434, 486, and even that 656. So Balmer discovered the equation. And of course, at that time, he doesn't know. He did not know. He did not know the reason behind. He only know the equation. And of course, this is already very, very great. Well, later on, the scientists, they understand what happened inside the hydrogen atom. Would you copy that down as well, alright? So draw a nucleus here, and then draw a few different circles to represent the orbits of electron. You know what? The electron should be here. It was here, electron. Here, there we go. The innermost electron shell. You know, hydrogen, there is only one electron. And then that electron orbits around the nucleus. The nucleus has only one proton. However, this electron is somehow excited. And then it may go to other electron shells such as this. Like that, alright? So maybe the electron absorbs the energy and then it is excited to this shell, the 5th electron shell. And then later on, it falls back to the lower energy level electron shell. For example, just like this, the electron falls and then it go back to here. And then in this way, it may produce a wavelength of light corresponds to that frequency, correspond to that energy change. Alright, so one more time, let me explain what I mean is electron may be excited first of all, and then later on when it falls back to the lower energy level, then it will produce light of certain frequency. So that's how the light is produced inside an atom. First of all, electron is excited. Secondly, the electron falls back to a lower energy level. And so, light is produced. Now let's see what the table tells us. Okay, so what the table tells us is the first one that I written down here, right, is indeed the electron transition from the 3rd electron shell to the 2nd electron shell, and then it produced the so-called the 1st emission. And then when it falls from the 4th electron shell to the 2nd electron shell, or from the 5th to the 2nd electron shell, then it will produce different colors of light. So, Balmer was lucky because he looked at the emission spectrum of hydrogen and then he identified these 4 different visible light, which are red, and then this one, blue and green, purple, alright, violet, alright, and the last one also violet. And then he find out, alright, these 4 different wavelengths, they are closely related. They have this very, very special relationship, alright? That one that is found on the upper part of the page. They are so related, and then there is only a constant, Rydberg constant, and then other people try to follow what Balmer has done. Other people, Lyman, Pestion, and Brackett, they try to copy what Balmer has done. They try to analyze the emission spectrum of hydrogen. The emission spectrum of hydrogen is so complicated. Balmer only analyzed the visible part. The visible spectrum part of the hydrogen spectrum is the easiest to be observed because it is visible. And then later on, Lyman even analyzed the UV part. And there are also people who do something more, such as the IR part, or well, that means they measure the wavelength of infrared, and in that way, then they can conclude these equations. Lyman find that he can change the 2, alright, into 1, and then Pestion changed the 2 into 3, and lastly, Brackett changed the 2 into 4, and then they form other equations as well. And all these equations you may generalize and then make it like this. You may change the n1 and n2 values in the equation, alright, appropriately so that you may calculate the wavelength of all other emissions.